6.2, we're going to be talking about this idea of a series. All right. So, yesterday we talked about things called sequences. The sequences were patterns with numbers, but in order to be an arithmetic sequence, you had to be adding the same number every time. So, plus 2, plus 2, plus 2, plus 2, and that number couldn't change. And we had geometric, which we were multiplying the same, times 3, times 3, times 3. Well, what happens when you have the same pattern with like a shape? Well, that is called a tessellation. Okay? Tessellation is where you have a pattern with the same shape repeated over and over again. There's a couple examples. Right up here, they give you an example of a tessellation. Okay? Technically, this right here, if you look at the definition, they need all the shapes to be touching. So you'd have to actually, you see these 1, 2, 3 hexagons? You see the hexagons? They should actually be smashed up against each other. But in art, sometimes they create a little spacing in between. What does this look like? Beehive? Honeycomb? Same kind of thing. What? A little flower? How about tile? Do you guys ever see tile? That's a tessellation as an example of tile, where we do little patterns sometimes for our ground. That would be an example of a tessellation, because you have that same pattern repeated over and over again, and everything butts up together. There's grout in between, but it would butt up against each other. So if you look, tessellations, it says there's no overlap and no gaps. So you see how there's gaps right here? In art, sometimes they put, for a tessellation, they put gaps just to make it a little prettier. But technically, if we wanted it to be a tessellation, these guys should be touching. So, do you see this side right here of this, the black one? Do you see the side of this one? They should share this one side right here. This side should be sharing. You get what I'm talking about? So like these guys right here, these toothpicks are arranged in rows. Do you see when they go to row 2, how this uses that side right there? They both use that. And when I go down here, this one uses these two from that, so it actually only adds 2 on there. You guys get what I'm talking about? Because they have to share sides. Okay? That's what a true tessellation should do. So, the first thing they ask us to do is a lot of 6-1 stuff and applying it to tessellations. Fill this table in real quick. Alright, so if I was filling this in, I should have 4, 6, 8, 10, 12. Okay? The next question that they ask us, can this tessellation be represented by an arithmetic or a geometric sequence? Explain how you know. Plus 2, plus 2, plus 2, plus 2. Is this an arithmetic or a geometric? Or neither. It is an arithmetic because I'm adding 2 every single time. So how can I explain that I know? Because I'm adding the same number each time that I go up. Okay, that would be enough explanation for me so I'd understand. Write an explicit formula for this sequence. Let n represent the row number, and let a n represent the number of additional toothpicks used to create that row. So, a n, what did our explicit formula say? A1 plus b times n minus 1. Now we just need to fill in all these things that we need to know. A-N is going to stay A-N. What is A1? How many toothpicks did we start off with in the first row? 4. So that becomes 4 right here. Plus, what's the common difference? How much did we go up by each time? And then n minus 1. Now, I'm done filling in. Do you guys know anything from Algebra 1 that you can do to combine like terms and simplify this equation even further? Yes, you do. What can you do with the 2? Everybody see where that came from? Do I have any like terms? Can this combine with this? No. Can this combine with this? So I'm going to pull this guy forward. Remember, the sign stayed with it when you pull it forward. So what sign is with the 2 in? A positive. So guess what? It stays a positive here. What is the sign of the 4? Positive. What's the sign of the 2? What happens when I have different signs? What have I told you to do? What do they do to each other? They cancel out. You do not add. This is a positive 4. You have negative 2. I just explained this to my kids in the car, and they're like, give us more, Dad, and they were doing it right. I have my first graders going, I'm getting it down, I got it, Dad. Okay, here's what I explained. How many of these do you have? You have 4 positives. You have 2 negatives. What do these guys do to each other? So am I really adding? No. This cancels out. This cancels out. What am I left with? 2 positives, so plus 2 right here. Alright, so if I wanted to figure out how many additional 2, now listen, please understand this because this is where you can kind of get tricky with this question. Number of additional toothpicks. Is this saying how many toothpicks are in the creation total when I'm at row 5? No. It's how many additional toothpicks I need to add a 5th row. So if I wanted to add a 6th row, I would need 14 more toothpicks in order to be able to create that 6th row. Do you get the question? So it's not how many total are in that whole creation when I have 5 rows. We're going to talk about that today in just a second. Okay? So that's why I'm saying keep that in mind. So how many additional toothpicks will he need for an 18th row? This is not how many toothpicks will he need to make this creation with 18 rows. Do you get the difference? It's how many he will need just for the 18th row. So what is going to go in for my in? So all I'm going to do is go 2 times 18 plus 2. Finish that for homework. I know that's going to take you so long. Please don't finish it now. I know it would be, way too hard. All right, this is the big part. This is going to be the big part. We're getting into something that you've never probably seen before. This is going to be a new topic, and it is called a series. Okay? So a series. We use these a lot. They are not a big deal. A series. So we've got a special notation. And this symbol right here is sigma, and it's going to represent summation. Summation just means when you add a whole bunch of stuff together. And I'm gonna show you how you know what you're gonna be adding together. So this right here tells me, so if I have a list, let's just give it, sometimes showing an example of what's gonna happen and then going back will be easier. So I'm just gonna give you a quick example. If I gave you a sequence like this. Does everybody see my sequence? Okay. If I wanted you to add all these together, that would be called a series. Where I'm saying I want the first one plus the second one plus the third one. How much total is that all together? That is what the idea of a series is going to do. But I need to tell you, because doesn't this series keep on going, or doesn't this sequence keep on going forever? So in a series, I need to tell you where I want you to start and where I want you to end. That's what this notation over here does. Does that make sense? You guys follow me? So, this right here is going to tell you what series you're doing it to. So if I was doing this one, it would be S what? 1, 2. So it would be a 3 here, because that's where I want you to stop.
So it's like calculating mean.
No, because we're not dividing by anything. We're adding everything up. Mean, you would add them all up and divide by how many there are. no division in here. We are adding them all together. So, do you remember in this example right here, where I told you this would complete row 1, this would complete row 2. How many would I need to complete row 1 and row 2 together? 10 toothpicks. How did I know that? I completed this series where I added the first row and the second row together to know how many total toothpicks I would need. That's what a series does. Do you understand what I just said?
A little bit. So like, if you're like gonna go to the 36th row, how would you do that?
It's going to take a long time. Because you're going to need, with a calculator can actually, like those graphing calculators, can actually do summations with a formula, and you can pop it in, and they can add it all together. But without a graphing calculator, you would have to first find every one of these all the way up to row 36. Then you have to add all these together.
So it just depends on where you're starting and stop.
Right, which I won't give you one that goes all the way to 36 on a test. We would never do that. But you can do that in real life. People do that. But you use a calculator. So here's what happens. When I give you this notation, this just tells you you're adding them all together. This E just tells you you're adding them all together. This I equals 1 is your starting point. This number up here is your ending point. Meaning, if I said from 2 to 3 here, then you'd only add the second number of the series and the third number of the series. We do a couple more examples, this should make sense. And then this just represents all the different ones. We'll talk about that in a second. Do you see down here how it says in other words? Do you see this down here how it has from I equals 1 all the way to n? Because remember, n can be any number. You keep going from A1, you add A2, you add A3, you add A4, you add A5, you add all the way up until you get A to the whatever that is. If it's a 10, then you're going to have 3, 4, 5, 6, 7, 8, 9, 10. And remember, all these represent are subscripts. That's the first number of the sequence. That's the second number of the sequence. That's the third number of the sequence. Are you following me? All right, so let's go to some of these right here. Use sigma notation to rewrite each of the finite series and then compute it. Okay? So if I was going to do this, sigma notation would say, here's what I need plugged in. Where am I starting at? I is going to be the first one still. And where am I going to end at? Where does it tell me I'm going to end? And that's an I. So what does this really mean? I'm going to take A1 and add it to A2. Do you see how this right here represents all the ones between 1 and 2? Do you get what I'm saying? Yes, ma'am. From right here. So all this represents is it's saying it can change. This is going to represent all the values between here and 2. So that's why it became 1 and 2 over there. The I. Are you guys following along with what I'm saying? And like Matt said, all you do is you go, A1 is the first number in the sequence, which is 5. A2 is the second number in the sequence, which is 9. And so if I wanted the summation of that, it would be a total of 14. If I was doing this one right here, if I was doing this one, it would be sigma, which means summation. I'm going to start at my first one, so I equals 1. You always got to define that. This is just a variable. Doesn't always necessarily have to be I. For this book, we're going to use I, just so you're comfortable with it. But it's just a variable. And we're going to go all the way to what here? And that's still with AI. So I'm going to, what does this really mean? It means I'm going to take A1 plus A2 plus A3 plus A4, add A5, which means all these are is the first number in the sequence, second, third, fourth, and fifth. And if I look at that, it's 5 plus 9 plus 13 plus 17 plus 21. So they actually just 1, 2, 3, 4, 5. They just took and added all these together. And if I do that, you should get an answer of 65. Does everybody kind of understand what we're talking about here? All right, so for homework, I want you to go ahead and try part B. And now we're going to kind of skip over something for just a, I'm going to go through it really quick with you. So actually, do number 8 too. Number 8 goes back to using those toothpicks. And if they had said, that's good. That goes back to those toothpicks. All right, so this guy created, he created a way for us, Gauss, to create this quicker, to add these summations quicker. So he did a real quick series just to give you an example. So please watch this real quick. The more we understand this, it's going to help us out for why he came up with this formula. This guy realized that if you take the first number in the sequence and the second number in the sequence, or the last number in the sequence, what does it add to? He did this series, 1 plus 2 plus, like the sequence here is he's going up by what each time? What is he going up by each time here? 1. Does that make sense? Okay. He did the same sequence, but he wrote it what way? This way. He wrote it backwards because he realized if you take and you add forwards with the backwards, watch what happens every single time. What does this add up to?
1.
What does this add up to?
1.
What does this add up to? He realized that if you wrote it forwards and you wrote it backwards, that it would always add up to this same number. How can that help me out? Well, how many times, since this series is all the way up to 100, how many 101s is he going to have? He's going to have 100 of them. Does everybody see what I just said? Because this series goes from 1 to 100, he's going to have 100 of these. And if he has 101 100 times, we can write that as the multiplication problem, 101 times 100. But there's one problem. How many of these series does he have? 2. How many does he only want to compute?
1.
So how can you solve that problem? Divide this answer by 2. Cut it in half. And then you'd have the summation of one of the series. Does everybody understand what I just said? This was Gauss, and this was his thought process. So, this is all explaining it. We're going to come up with the... So here's the formula, and then you guys can finish this for homework. This is the part that we really need to get right here. This is what we just discovered. If you take the first term and you add it to the last term, you get what every of the terms would have added up to. That 101 that we just discovered, right? And if you multiply it by n, what is n?
The term trying to get.
How many terms you're going to add up? Like, remember in that one, we went from there was 100 terms, right? So, whatever number you are on represents the n. And then why do we cut it in half? Because we only want, that's 2 of them, we only want 1 of them, so we divide it by 2. I'll finish this video, watching this video. Alright, so we're going to do, I'll have you do this one for homework. I'll have you try it. this one. I'll kind of set it up with you. If you think about it, this is Sn, so this would be S. Since it's the fifth row, it would be 5. And you would take, this N would be 5. The first number, A1, would be how many toothpicks we had at the beginning, which was 4, plus, and the number of toothpicks in the fifth one was 12, and all of that divided by 2. So you just finish that off. Hopefully you see where my numbers are coming from. You can finish that homework. Same with this kind of thing. If we wanted to do 18 rows, the first thing, if we look back at our chart doesn't go to the 18th row. So the first thing I need to do is figure out what is the 18th row, how many toothpicks are in the 18th row. So I first need to use my explicit formula, which if we remember what that explicit formula was, actually I'm sorry, you should have done that using that explicit formula for homework, so you should be able to look back and see the 18th row. He needed 38 toothpicks. So if we do that, go ahead and do that for homework. See if he only has 350 toothpicks, if he's got enough. Remember, like when you do the summation, it takes more than that, then no, he doesn't have enough. If it takes less than that, then he's got enough toothpicks. Okay, so you should be able to finish those two from homework. And one thing I want to make sure that we understand is this is summation, and Gauss's formula is only going to work in arithmetic. So it only works in arithmetic series. This does not work for geometric. We will study those in 6.3, which will be tomorrow, but this only works for arithmetic sequences. These are known as arithmetic series, so make sure you understand the difference between these. So here we go. We're going to keep moving on. All right, I like this problem. So it says determine the number of, write an explicit formula for the Nerman of odd whole numbers. So if I think about the first odd whole number, the first odd whole number is number A, again, equals, the first one is 1, plus the common difference. Every time I go up an odd, it's by 2, and it would be n minus 1. And so this would become 1 plus 2n minus 2, combine like terms. So my explicit formula would be 2n minus 1. That would find, if I wanted to know the fifth odd number, I could put a 5 in here and it would calculate the fifth odd number. The reason we need that is for our next question. It says use Gauss's formula to calculate the sum of the first 20 odd whole numbers. Well, I could figure out and I could write out every odd number all the way to the 20th one. So it'd be 1, 3, 5, 7, 9, keep going. And I'm only at 1, 2, 3, 4, 5, so I've got 15 more to go. Then I would have to take all those and add them together. Or I could use Gauss's formula that says the series and we're going to the 20th term. So for this, it would be S20 would equal n, where it's n, A1 plus AN all divided by 2, which equals, what row am I going to, or which one am I going to? 20th times the first one is 1, but when I get here, I've got a problem. I don't know what the 20th odd term is. If I go back here, this formula can help me find any row or any number in that sequence for that series. And I want the 20th one. I need to know the last. I need to know the 20th one so I can plug that in here. So sometimes you have to go back and use those formulas. So I have to figure out what my 20th one is. So I go 2 times 20 minus 1. 40 minus 1 is 39. And what I realized is if I counted this out, if I kept doing this and I kept going, my 20th one would be 39. I used my formula from right here to figure out the 20th odd number. So 39 divided by 2. 39 plus 1 is 40. 40 times 20 is going to be 800. And 800 divided by 2 equals 400. For the next question, I don't really want to go through what they did here, so question number 3, it says calculate first 100 odd whole numbers. Find the sum of that. I want you just to do it doing Gauss's formula. Don't worry about any of these stuff up here. I want you just to do that using Gauss's formula. So just to give you some hints, you're going to have to do the sum at 100. You're going to have to do equals what number n is 100 in this example, because I'm going to the 100th one. My first odd number is 1 plus an. I don't know that value, over 2. So you're going to have to calculate, using that formula from above, you're going to have to figure out the 100th odd number. So that's going to look something like this. It was 2 times 100 minus 1. And so that should get you started enough to where you need to get to. By the way, the answer for this problem should end up being 10,000. So I'm going to start putting the answers up there for you, because that way you should be asking me questions in class. We'll go back to that. You should finish this. You should learn how to get to 10,000. If you just put 10,000, yeah, you'll get points, but you won't know how to do it. All right? You should try number 4 for homework. Again, I'm going to try to skip this. The first thing I need to do is write an explicit formula for even numbers. Actually, scratch that. So actually, I'm going to go up and explain something real quick to you. Right here, they're going to show you a different way that you can use Gauss's formula. It says, you know that the series n equals n a1 plus an. Well, this an can represent the formulas that we have found to represent the series sequence. So in this example, what she wants to do is she's going to show for the first odd numbers. That meant that what we can do, instead of, if we don't have, if we want to solve it another way, we can come up with another formula by taking this and simplifying, going Sn equals n, and then a1 for this example was 1 plus, and if you look back at our an, that means you look up here at this equation. You see where it says an and it says equals this? So that means that anytime you see an, you can replace it with all of this. So what happens here is an now becomes, for this example, 2n minus 1. It becomes the explicit formula. So it becomes 2n minus 1. And then what we can do, still divided by 2, is you can distribute the n. And you can solve some stuff. So when you distribute the n, you get n plus 2n squared minus n divided by 2. Combine like terms. This n and this n cancel out, and then you're left with 2n squared over 2. The 2's cancel out, so what you're left with is really, you can just take n squared. So what happens is, this is the summation for the first, this is the summation formula that would actually be much easier to do. So like right here, when they say calculate the first 20 odd whole numbers, what you would do is, using this formula, all you have to do is, you can say that's the same as just taking 20 squared. And when I square 20, it gets me to 400. So it's just giving you another way of using Gauss's formula to come up with, instead of having to keep plugging every time and simplify, you can simplify Gauss's formula for everyone by plugging in the an, and then you have this much simpler formula to use. So let's try another example. I know this is a long video, but so if we did this one, and we wanted to write an explicit formula to calculate any term of the sequence of the even numbers. So if we just want a, they're just looking for a n would equal A1 plus T n minus 1. So in this example would be 1 plus 2, because we're going up evens in every other number, n minus 1. Distribute, and you get 1 plus 2n. Oh, I'm sorry. I lied to you. Here's where I went wrong. The beginning number, if we're talking about evens, my first number is 2. So this would be a 2 also. And then when I distribute that, I get a negative 2. This 2 and this 2 would cancel out. And so I'd be left with just 2n. So an equals 2. Now, take this, and they want me to come up with for Gauss's formula, a simpler way to just calculate it anytime. So here's what I would do. S and summation for Gauss's formula is n a1 plus an divided by 2. Well, see, for this one, this allows me to use it for any row or whatever, or any number in the sequence. Because remember, if I have like 8, 10, 12, 14, this is like what I was referring to as row 4, or the number 4, the fourth number in the sequence. That's the n. So if I wanted this to be any number, any term in the sequence, what I can do is I can solve like this and plug it into right there. So here's what that looks like. And A1 is still 2, because we're in the new one, we're in the evens, so my first number for even is 2, plus 2n over 2. Distribute, and you get 2n plus 2n squared divided by 2. Well, 2 can go into this, 2 can go into this. This cancels out, this cancels out. What I'm left with is really n squared plus n. That would give you the summation for any of those. So, if I use my function from right here, I can go, and I'm saying, what I'm telling you is if you wanted the first 100 even and you wanted them all added together, you could take 100 and square it and add 100 to it. And that would be equivalent to just like if I use Gauss's formula the other way, which is where I do n times a1 plus a at 100. And now I actually have to calculate what a at 100 is and divide it by 2. So I want you to try that for homework. Try verifying this is equivalent to this.